Hey everyone, today we're going to do our formal lesson on what is called VSPER theory. So last week we looked at some three-dimensional shapes of covalent compounds, and today we are going to formalize that. That process is called the VSPER theory, and what that is, it stands for valence shell electron pair repulsion. And really, this is just putting a name to drawing the Lewis structure and determining the compound's three-dimensional shape. So what we're going to do is we're going to draw our Lewis structures and determine what is the 3D shape of a compound. We are going to be filling out a table today. As you can see, I don't have a printer and I just copied a table down. So if you need to pause the video and create your table, now would be a good time to do so. Before we even talk about Lewis structures, we have to get a little background on the three-dimensional shapes that can be formed. What's important to know is that atoms want to spread out as far apart as possible from each other. Remember, they're surrounded by electrons, which are negative, and so atoms want as much space as possible to keep their electrons away from each other. So let's look at the different shapes that things can form. If we look at what's called a binary covalent compound, remember the prefix bi? That just means two. So that means a covalent compound with just two things. So that might be something like our two fluorine atoms. So if we have two fluorine atoms, then they're going to be in a linear shape because 180 degrees is the farthest apart that these two can be from each other. This is similar if we have a central atom with two things around it. And I put quotes around the word things because that can be either electrons or atoms. So let's say I have a center atom. I'm just going to call it A. And the farthest apart that two things around the center atom could be, again, is a line, 180 degrees. So if something has two things around it, the farthest apart they can be from each other would be in a shape called linear. Now let's add one more thing around our central atom. So if we have three things around our center atom, again I'm going to call that center one A, then those three atoms are going to stretch out in each direction. As far as apart as they can be from each other. Now, what you should know is that these are all in the same plane. And what that means is that if we were to lie this flat on a table, nothing would stick up. Okay, they all lie within the same plane, kind of like this paper. And you don't need to know these bond angles, but if they help you because you're a pretty mathematical thinker, these angles are 120 degrees from each other. If you think about it, we have 360 degrees in a circle, so if three things are stretching out in either direction as far from each other in kind of this triangle shape here, they're each going to form 120 degree angles. Now let's look at if we have four things. Remember, we have 3 dimensions to move, not just 2. We have 3 dimensions. So when we have 4 things around our central atom, they're going to form the shape called a tetrahedron. And what that looks like, how we draw it, we have 2 things kind of bent from each other, and then one thing coming straight out towards us, and then one thing kind of sitting in the back here. So this is kind of like a triangle base here, like a triangle pyramid with something sticking out of the top. So this is a shape called a tetrahedron. 4 things spreading out in 3 dimensions as far as they can from each other. And if it helps you, each of these bond angles are 109.5 degrees from each other. Again, it's not 360 divided by 4 because these are sticking out into different dimensions. These are all on the same plane, but if we were to lie this on a table, we would have this atom coming up straight towards us, whereas these two would be lying on the flat on the table. So what we are going to do is we are going to use all of these 3-dimensional shapes to help us determine the 3D shape and the names for different Lewis structures and for different covalent compounds. Like most things in chemistry, the vocabulary is a lot more difficult than the actual process. So pause the video as needed to fill out this table. And it's a good idea to have this all in one spot so that when you're doing practice, you have something easy to reference. So let's start out this chart. Each column here, so we have the total spaces filled around the central atom, the Lewis structure, number of bonded atoms, number of electron pairs, what we're going to call the VSPER code, the 3D shape, and the shape name. So let's start off with our binary covalent compound. And this one's kind of an exception here. It's not going to fit the rest of the pattern, so that's why we're going to put it at the top. And I'm just going to use A's and B's here. But the Lewis structure might look something like 2 atoms bonded together. Remember, bi means 2. So we have 2 things bonded together. We're going to ignore these here, and our VSPER code will be, we just have A and B together. So as we stated before, if 2 things are with each other, they form a linear shape. So our 3D shape will just be in a line, and this is called linear. And this is very similar to if we have 2 spaces around our center atom. So that's an example like here, when we have 2 atoms bonded to our center atom. So we're going to use A for our central atom and B to represent 2 things bonded to that. So looking at this Lewis structure here, the number of bonded atoms would be 2. And if we look around A, there are no electron pairs. So that's going to be 0. So we look at these to write what we call our VSPER code. And A is our center atom, and it's connected to 2 bonds. So AB2 would be our VSPER code. Our 3D shape, when we have 2 things bonded, would be, again, linear. So now let's look at if we have 3 spaces around our central atom. And there are 2 different scenarios that we can have. If we look at a Lewis structure, we could have 1, 2, 3, or we could have our center atom with a pair of electrons and 2 bonds. Both of these things have 1, 2, 3 things around the center atom. So let's look here. For our first one, we have 1, 2, 3 bonded atoms and 0 electron pairs around A. So our VSPER code would be A and then 3 B's. So AB3. Remember back when we drew 3 things spaced out from each other, and they formed this kind of triangular shape around our center atom. So when we draw that, we can draw that shape here, and this is called trigonal. Think tri as in 3, and planar because they're all in the same plane. So 3 things in the same plane. Now if we look here, this is slightly different because we have 2 bonded atoms and 1 pair of electrons. So this VSPER code would be A for our center, 2 B's for our bonded atoms, and then we're going to put an E to represent that pair of electrons. Now, to draw the 3D shape, we still have 3 things around our center atom, and they're still going to have 120 degrees. But the electrons do not get counted. They get counted in how the angles are formed, but the shape name changes based on if there are electrons there. So if we cover that up to represent a pair of electrons that are in that spot instead of an atom, notice how the 2 bonded atoms, how they look. They form a shape, and that is called bent. So we have our bent shape. We're not going to see this one too often. So let's look at our examples if we have 4 things around the central atom. Our first Lewis structure, we could have 4 atoms bonded, or we could have a pair of electrons and 3 bonded atoms. That still counts as 4. Or we could have 2 pairs of electrons and 2 bonds. Filling out here then, we would have 4 bonded atoms, 0 pairs of electrons. Our code would be A, and then 1, 2, 3, 4, AB4. And let's do these ones here. So we would have 3 bonded atoms, 1 pair of electrons, and here 2 bonded atoms and 2 pairs of electrons. This code would be A, B3, E, and this one would be A, B2, E2. They look a little strange, but it's just referring to the bonds and the electron pairs. So our 3D shape for 4 things, remember they form this tetrahedron shape. So we can draw the 3-dimensional shape. And this would be called tetrahedral with all 4 of them there. Now, if I cover up one of those spots here and there's a pair of electrons there instead of a bond, what you'll notice is it still has that same triangle base, and it's kind of in the shape of a pyramid. So this one is called trigonal, as in 3, pyramidal, because it's in the shape of a pyramid. So we have A, B, and trigonal, pyramidal. Lastly, if we have 2 pairs of electrons there, now we can cover up 2 of those, and what do you notice the shape is? See how it is bent. Okay, those 2 B's are bent away from each other. So those electrons are pushing everything away there. So this one is called bent. All right, so keep this table handy, keep it organized, and so you have a reference sheet. Let's do a couple examples. So if you have to determine the three-dimensional shape, your first step is to draw out the Lewis structure. So here we have CH4, and carbon has 4 valence electrons, and each hydrogen is 1. There's 4 of them total. So our electron budget is 8. So we have 2, 4, 6, 8. So if I look at this carbon, I have 1, 2, 3, 4 things around it, and they are 4 bonded atoms. So if I go into my 4 category here, and I have 4 bonded atoms with no electron pairs, so that VSPER code I can write down as AB4, and that shape is tetrahedral. So our code is AB4, and we have that tetrahedral shape. If we do HCl, we have 1 electron here, 7 here, and this is a binary compound here. Our code would be just AB, and that would be in the shape linear. If we do BH3, if I look on the periodic table, boron has 3 valence electrons, and each hydrogen has 1, for a total of 3. Remember, boron is the exception to the octet rule. So we have 2, 4, 6. Everything is good there. Our code, well, we have a center atom with 3 bonded atoms around it, no electron pairs. So if we have 3 things around it, all 3 of them are bonded, 3 bonds, no electron pairs. Our code is AB3, and our shape is trigonal planar. And lastly, water. So oxygen has 6 valence electrons, hydrogen has 2 total, with the 2 hydrogens there. We have our oxygen, our 2 hydrogens, and our 2 electron pairs there. There are a total of 1, 2, 3, 4 things around this oxygen. So if we go to our table, we have different options for 4 things, but we have 2 bonded atoms and 2 electron pairs. So our code would be A, B2, E2, and our shape is bent. So our code, our central atom A, 2 bonds, 2 electron pairs, and our shape is bent. So as we talked about in the lab, the three-dimensional shape is really important for covalent compounds because it determines the different properties about it. So different three-dimensional shapes tell us different characteristics about each of these compounds. So your next step is going to be to complete some examples and complete the lesson check, and be sure to reach out if you have any questions.